Hello everyone, welcome to the lecture series of pattern classification. I am Kundan Kumar, and if you would like to have these lecture slides, you may refer to my GitHub page at this given link. In last lecture, we have studied the discriminant functions and also we have studied the Gaussian distribution for univariate, bivariate and multivariate density functions. So now in this lecture, we would be discussing the discriminant functions for the normal density function. So here we will focus on the multivariate normal density function. So in the last class, we have derived the discriminant functions for minimum error rate classifier, which is given by GIX equal to ln likelihood plus ln prior probability. Now, let us assume that the class conditional probability density Px given omega I follows the Gaussian distribution, and for that we will derive the discriminant function using the multivariate normal density function. So here we are assuming that class conditional probability Px omega I, that means this is the class conditional probability of ith class, it follows a Gaussian distribution with mean I and covariance I, that means for I index is for the class. Okay, so we can compute the discriminant function GIX for this normal distribution. Okay, so what is the normal distribution for multivariate case? We have seen that P of x given omega I. Okay, so I am writing this one for ith class. So it is 1 by 2 pi the power d by 2 discriminant of the covariance of power 1 by 2 then exponential minus 1 by 2 into x minus mu I transpose sigma I inverse x minus mu I. Okay, so this is the multivariate normal distribution function, and already we have seen this equation in the last class. And also we have studied and we have discussed that if we take the logarithmic of the discriminant function, then it will not change our decision at all, because the logarithmic function is a monotonically increasing function. So if we will apply any monotonically function to a other function, then it will not alter the function characteristics. So here we will take the logarithmic. So ln Px given omega I equal to, so if we will take the ln of right hand side, we will get minus d by 2 ln 2 pi minus 1 by 2 ln sigma I determinant minus the inner term of the exponential. So now this is our equation 1. Okay, and what was the equation for the discriminant function that we have seen? So it was Gix equal to ln p of x omega I plus ln p of omega I. So in this discriminant function, we will put this value and then we will get Gix equal to minus 1 by 2 x minus mu I transpose sigma I inverse x minus mu I minus d by 2 ln 2 pi minus 1 by 2 ln determinant of sigma I. So this was the ln px given omega I and plus ln prior probability. Okay, so this is our the discriminant function. So remember this relation. This is very important relation. Okay, so here this is the same result that is written here. So now based on this type of distribution for different classes, we can have the different cases, like we can have the covariance of the two class as same, and we can have the covariance of the two different class as different value. Okay, so we can make here 3 different cases. Let us discuss one by one. Case 1. And case 1 is if the covariance of different class is equal to the sigma square I, and here sigma I equal to, that means covariance of ith class is equal to sigma square I. That means covariance of I is proportional to the identity matrix, and the covariance of each class is equal. Okay, so we can put this condition in our discriminant function that we just derived in this equation. So this is our equation 2. Okay, so put sigma I equal to sigma square I in equation 2. Then we will get Gix equal to minus 1 by 2 x minus mu I transpose sigma square I inverse x minus mu I minus d by 2 ln 2 pi minus 1 by 2 ln sigma square I plus ln p omega I. Okay, and here we can observe that these two terms are independent of I, because I is the index for the class level. Okay, so this is independent of I, so we can drop this term from the discriminant function because it will not contribute anything to make the decision. Okay, so our discriminant function will become minus 1 by 2 sigma square, because here I inverse will be I and sigma square, it will go in the denominator. So when you will solve this matrix operation, then I will be dissolved and you will get x minus mu I into x minus mu I. Okay, and plus this term. So ln p of omega I. Okay, so just solve it. So Gix equal to minus 1 by 2 sigma square x transpose x, just we are multiplying these two brackets, minus 2 mu transpose x mu I x plus mu I transpose mu I plus ln p of omega I. Okay, then we can write Gix equal to minus 1 by 2 sigma square x transpose x minus 1 by sigma square, because the 2 will be cancelled, and then mu I transpose x minus 1 by 2 sigma square mu I transpose mu I plus ln p of omega I. Okay, again this term is independent of I, so we can drop this. So now Gix equal to, so here it will be plus, then we will have 1 by sigma square mu I transpose x minus 1 by 2 sigma square mu I transpose mu I plus ln p of omega. Okay, and if you will observe this equation, then this is a linear equation. Okay, this is linear function of the variable x. Okay, so if we write discriminant function Gix as a linear function as wi transpose x plus wi0, so we can write this one because this is the x coefficient, so this term will be our wi transpose and this term will be our wi0. Okay, so we can write wi0 equal to minus 1 by 2 sigma square mu I transpose mu I plus ln p of omega I. Okay, and wi will be 1 by sigma square omega I. Okay, and here this wi0 is a bias or threshold for ith class. Okay, so this was our the discriminant function. Similarly, we can have the decision boundary between the two class. And we have seen that the decision boundary is defined as g of x equal to g1x minus g2x, and if this is equal to 0. So this is the equation of decision boundary. So whatever we have derived, we will put in this equation and we will try to find the equation of the decision boundary. So now we will have gx equal to wi transpose. So instead of the 1 and 2, we can make it gix minus gjx, so that the expression will be very general. Okay, so in place of gix, we can put wi transpose x plus wi0 minus wj transpose x minus wj0. Okay, and this is basically equal to 0. So now we can write, we will put the values. Okay, we will put the values of these parameters. Then we will have 1 by sigma I square mu I transpose x minus 1 by 2 sigma I square mu I transpose mu I plus ln e of omega I. Okay, and for this term it will be minus 1 by sigma I square mu I, this will be mu j transpose x plus 1 by 2 sigma square mu j transpose mu j minus ln p of omega j. Okay, so keep in mind that this omega j is the weight, okay, which is written up right letter, and this is omega. So this is basically w and this is omega j, which represent the class level. Okay, now we can write, so this will be 0. Okay, now we can write 1 by sigma square into mu I transpose minus mu j transpose. So this term and this term we will take the common, okay, and it will be this one. Okay, so now we can write minus 1 by 2 sigma square mu I transpose mu I minus mu j transpose mu j, and this is because of this term and this term, and the rest two term can be combined in ln. Okay, equal to 0. Okay, now we can write as, that means we can multiply both sides with the sigma square, then this expression will reduce to mu I transpose minus mu j transpose into x minus, so here also sigma square will vanish, and mu I transpose mu I minus mu j transpose mu j, okay, plus, so here sigma square will be multiplied, so ln p of omega I divided by p of omega j, and this is equal to 0. Okay, so from this expression we will take the common mu I transpose minus mu j transpose. Okay, so take the common this term, it will be mu I transpose minus mu j transpose. Okay, and the rest of the term, so it will be x minus 1 by 2 mu I transpose mu I minus mu j transpose mu j divided by mu I transpose minus mu j transpose plus sigma square divided by mu I transpose minus mu j transpose. Okay, and ln p of omega I divided by p of omega j and equate to 0. Okay, and this expression will reduce to mu I transpose minus mu j transpose, okay, into x minus 1 by 2. So when you see the numerator term, then this term will be common in that, and we will have the mu I plus mu j. Okay, because this is the square term, so a square minus b square, then it will be a minus b into a plus b. So a minus b will be cancelled and a plus b will be remain. Then plus sigma square, and we can write this denominator term in terms of norm, so that we have to multiply the other term, and that term is mu I minus mu j. So these two are equivalent. So we got this expression. Okay, so if you will observe this expression, it has also some standard form, and we can write this in standard form, that is W transpose into x minus x0 equal to 0, where if you compare, then W is mu I minus mu j and x0 equal to 1 by 2 mu I plus mu j, okay, minus sigma square divided by, so here it will be square term, mu I minus mu j square ln p of omega I divided by p of omega j into mu I minus mu j. Fine. So from these two equations, we can have some observation that here it can be noticed that the inner product of weight vector W, okay, so inner product of weight vector W and x minus x0 is 0. So the separating plane is perpendicular to the weight vector. Okay, so whatever the weight vector we have, and this is the separating, these points is in the on the separating plane. Okay, so we can say that W is perpendicular to the x0. Okay, because here W is not a zero quantity, so definitely x minus x0 will be 0. So x equal to x0. That means this decision boundary will pass through x0. That means x0 lies on the decision boundary, and W is the weight vector which is perpendicular to the decision boundary. In other way also we can say that if you will observe this expression, then we can say that the weight vector W is in the direction of the line joining the two means of the class I and class J. Okay, so from these two conclusion, we can conclude that our decision boundary is perpendicular to the line joining the two mean of the class I and class J. Okay, understood? So here we can see an special case, and that special case is that if the prior probability of all the classes are same. So in this equation, if the prior probabilities are same, then these term will be equal to 1 and this complete term will vanish. Okay, that means our decision boundary will pass through the bisector of the two mean of class I and class J. Okay, so here our decision boundary will pass through the perpendicular bisector of the two mean of class I and class J. Okay, and this condition, that means is this, for this particular condition we have a particular type of classifier, and that classifier is called the minimum distance classifier. Okay, so minimum distance classifier says that when p of omega I are same for all the classes, that means I equal to 1 to C, then the designed classifier is called minimum distance classifier. Okay, where W equal to mu I minus mu J and x0 will be mu I plus mu J. So our decision boundary will be W transpose x minus x0 J. Okay, so W transpose into x minus x0 is the decision boundary, where W equal to mu I minus mu J and x0 equal to 1 by 2 mu I plus mu J. So now we can define our decision rule as assign x to omega I when I equal to argument of minimum for I equal to 1 to C and the minimum of the Euclidean norm. That means we will compute the distance of x from the mean of all the classes, and we will select that class from which our feature vector is closest. Okay, so we will select the ith class if it will be closest to I. Okay, so this is our minimum distance classifier. Now let us discuss the case 2. And the case 2 is sigma I equal to sigma. That means the covariance of the two class is same. Okay. Of fine. Okay. we know that Gix equal to minus 1 by 2 x minus mu I transpose sigma I x minus mu I minus d by 2 ln 2 pi minus 1 by 2 ln determinant of sigma I plus ln p of omega I. Okay, so we will put sigma I equal to sigma, then we will get Gix equal to minus 1 by 2 x minus mu I transpose sigma inverse x minus mu I minus d by 2 ln 2 pi minus 1 by 2 ln determinant of sigma plus ln p of omega I. Okay, so again these two terms are independent of I, so we can drop these two terms. So we will have the discriminant function Gix equal to minus 1 by 2 x minus mu I transpose sigma inverse x minus mu I plus ln p of omega I. Okay, so we can write Gi of x equal to minus 1 by 2 will be x transpose x minus 2 mu I transpose sigma inverse x plus mu I transpose sigma inverse mu I. Okay, and plus ln p of omega I. Okay, and then we can write Gi of x equal to, just expand this term, plus mu I transpose sigma inverse x minus 1 by 2 mu I transpose sigma inverse mu I plus ln p of omega I. Okay, so this term is independent of I. Again we can drop this term because it will not contribute anything to make the decision. So we will have this term only. Okay, so let us write the discriminant function Gix equal to mu I transpose sigma inverse x minus 1 by 2 mu I transpose sigma inverse mu I plus ln p of omega I. Okay, so if you will observe this discriminant function, this has a linear form. Okay, so this is the linear discriminant function. So we can write in the standard form as wi transpose x plus wi0. Okay, where wi equal to sigma inverse mu I. Okay, because wi is equal to sigma inverse mu I. So wi0 equal to minus 1 by 2 mu I transpose sigma inverse mu I plus ln p of omega I. Okay, and if we will solve for the decision boundary as we have solved in the case 1, we will get so here I am not going to solve the decision boundary for case 2 because it is quite similar to the case 1. So I am directly writing the decision boundary that we can obtain using these two discriminant functions. Okay, so this is our decision boundary where W equal to sigma inverse mu I minus mu j, x0 equal to 1 by 2 mu I plus mu j minus ln p of omega I divided by p of omega j divided by mu I minus mu j transpose sigma inverse mu I minus mu j. Okay, and into mu I minus mu j. Okay, so here our decision surface passes through x0. Okay, from this expression it is clear, but it is not necessary that it will be orthogonal to the line between the means. Okay, it is not necessary. Okay, now let us discuss the case 3. Okay, where sigma I is arbitrary. That means the covariance of the different class are not same. It can be anything. Okay, so we can derive the discriminant function for this case as well using the same discriminant function of the normal density function, and we will put this case and we can derive the expression, and then we will get the discriminant function as gix equal to x transpose w, here this is capital W, to x plus wi transpose x plus wi0. Okay, so this is basically the quadratic form. Okay, where wi equal to minus 1 by 2 sigma I inverse, okay, and small wi equal to sigma I inverse into mu I, and wi0 equal to minus 1 by 2 mu I transpose sigma I inverse mu I minus 1 by 2 ln determinant of sigma I plus ln of p of omega I. Okay, so in this case also we can find the decision boundary, and that decision boundary will be hyperquadratic. Okay, so that is very complex equation, so it is not required now, that is not in our syllabus, but just we should know that decision boundary in this case will be hyperquadratic. Okay, in the next class we will solve some problem on these distribution, and also we will consider the Bayesian decision rule to find the equation of decision boundary. Okay, and then we can make the decision.